with 2/3 of the world already living in urban areas, and in many developing countries, this number closer to 85, almost 90%, that the importance of urban areas in the global economy and in terms of resiliency and in terms of quality of life can't be overstated. So it's always been of an interest to me that in the past decade, as we've talked about smart cities, that in many ways the city itself, the physical city, has somehow been overlooked. That much of these initiatives and discussions have been about moving objects, systems, but the actual infrastructure, what we walk on, what we come in to, what we go out of, where we live, where we work, seems to have been forgotten. I came to this issue of how do we physically model these physical systems in a bit of a funny way. As Rob kindly mentioned, my training is actually in civil engineering, in particular in geotechnics. And I had a good fortune when I was doing my PhD at the University of Illinois back in the 90s to come over to London and to get to see a lot of the construction as part of the Jubilee line. As you may or may not be aware, at the time it was the largest underground construction in the world. It was a £2 billion project, and 25% of the £2 billion went to the prediction, protection, and monitoring of buildings for building damage due to ground movement. And despite this enormous investment, a lot of buildings were damaged. So the question then became, what's going on and why are our computational models not working? And what we found in talking to engineers from MOTS and ACOM and ARPS and a lot of the other companies that were involved with this was that it wasn't that the computational models weren't good, it's that they couldn't use them because they did not have the geometry of the built environment for the thousands of buildings along the tunnel route. And over the next few years, as I finished my PhD and started to work as a junior faculty member, I realized that this was a problem that if we as a community wanted to move forward in tunneling, we had to solve. And I had the good fortune of meeting Dave Bloomquist from the University of Florida, who was the one who actually flew the plane over the World Trade Center bombing site to help prioritize debris removal. And as part of that, not only were the heat image mapping done, but there was LiDAR. And I started to look at a lot of this data, and I said, well, why couldn't we use this type of data to auto-populate city-scale models? And you could think about this from the building information modeling side, where we're just building models for individual buildings extending all the way across the city, or on the other side of things, actually from computational modeling. And when I started getting involved with this very fully about 10 years ago, people said, oh, there's all this work that's been done. You know, and I said, if you look at what's been done, it's mostly in gaming and Hollywood, and these images, these models, they look great, but they're not usable for engineers. They're not geometrically accurate. They don't represent the physical materials in the built environment. They're immutable. There were a series of problems. And so I set about the goal of trying to develop systems that could populate these models both above ground and below ground in terms of things that were truly scalable and robust. Because most of the solutions that were out there, even if they were largely automated, were not appropriate from one community to the next. And what I mean by that is what works for London isn't going to work for Lisbon or Lima, Peru. So we started from kind of the concept of how do you collect all this data and how do you think about then harvesting it, harnessing it, and having it available basically for reuse. So the long-term plans, you can think about lots of different aerial sensing that comes in from helicopters, planes, drones, and obviously the newest was through auto navigation systems. And how do you store this in something beyond the typical GIS system, you know, moving out of a 2D layering mentality into something that's fully queryable both spatially and temporally. And when we started this and kind of think about kind of 10 major challenges from very simple things on data quality and data coverage all the way down to the final storage. And what we'll talk about ultimately is that a lot of this is going to require some heavy lifting from the computing community, because the size of these data sets is just becoming increasingly enormous. So for example, what you're seeing here is actually a 1.5 square kilometer area for Dublin, Ireland. Over on the right-hand side is Trinity Campus. Under the helicopter in the center is Grafton Street, and it leads you up the northern border is actually the Liffey River. So this section, when we did this in 2015 with a little bit of data around the sides, between our LiDAR data, so our laser scanning data, both the discrete and full waveform, imagery, and a few other bits and pieces, ends up being about 2 terabytes per square meter. If you take that across a city like New York, we're talking about a petabyte. So my brother works for Google. He says, what's a petabyte between friends? The storage isn't the problem. It's the indexing and querying it, because we can't just keep trawling through it. So then the question becomes, how do you integrate this data in a meaningful way to harvest the investment of so many different agencies as well as private companies for the betterment of the cities? And what you'll see below is some of our initial work taking this concept that these cities, even very dense ones, even quite tall ones like New York or London, actually are quite spatially wide compared to their depth. So what we do is we actually do a 2-part layer. We've got a Huff transform on top in the bottom right-hand corner, sitting on top of a series of octrees, where we're doing the 3D data indexing locally and the 2D across the top. And it's kind of an initial step towards really taking advantage of distributed computing environments. And we'll come back to this kind of at the end. To start with this, we had to rethink how data was collected. So if you're familiar with laser scanning and a lot of these other remote sensing systems, they tend to be hung off the bottom of an aircraft, and they face downwards. So laser scanning in particular was set up for floodplain mapping, and if you're trying to map a road, a roof, a mesa, they're really great for that. But because the equipment's facing down, and you're therefore only getting facade data in the oblique portion of the swing of that. So if I've got 100 points on the ground per square meter, I'm only getting about 10 points per square meter on my building. And so you can see when we started this in earnest in 2007 that the quality of the data on the facades was quite low. So we did our first scan with Fugro in Dublin in 2007, and we sat down with them and we said, we want you to fly things differently. And they said, oh, well, we always fly the same way. We fly along the street, we turn around, and we fly back, because that way the pilots know where they're going. I said, well, that's great, but you're actually causing more problems that way. And we just said, okay, as just an initial step to this, we want you to go at 45 degrees to the general grid of the city. And they said, well, that's really weird. And I said, really, the geometry will play out. And by doing this, we're able to pick up twice the number of facades in every single pass. So just some very simple things, not even increasing the flight time, we're able to increase that density of data. The other thing that we've been looking at is how do we harness a lot of the existing technology. So the equipment's getting better, and we're getting greater densities, but what we're also doing is we're having access to more of the raw data, and in particular, the full waveform version of this. So we've recently released this data. It was actually released last week through NYU's library site, and it's the first major urban full-wave LiDAR data set, and it's available for anyone who wants it. And what this does is the full waveform gives you the full energy backscatter for every point. So the laser scanning, when you get it commercially, you get basically a series of discrete points. They're X, Y, Z positioned based off a global positioning system, and you get an intensity value, which is an indication of the energy backscatter. In the full waveform, which you'll see here, we've got a series of these kind of smashed together. We've got a sense of how much energy is coming back with each of them. And no one has ever gone into and really looked at how to harvest the full extent of this. Commercially, what's been done is that each of these major producers like Regal develop an in-house system that is supposed to pull out the greatest intensity point in here, and that they affiliate with a solid object. But the problem is that the traditional ways of doing this through a Gaussian, assuming a Gaussian distribution, prevent us from fully harvesting that it only allows us to find objects that are a minimum of 60 to 70 centimeters apart because of how the equipment is working. But by partnering with people in electrical engineering and borrowing from the signal processing community and using sparse deconvolution, we're able to get that down to about 1/4. So the most recent work, and this is not yet published, that we've been doing in this area actually allows us to get the distance of about 15 centimeters to about a 2 to 3 centimeter accuracy. So all of a sudden, when you're thinking about this data, it's being collected, in our case, from about 300 meters in the air, and that spot's coming down on the ground. So by the time it gets to the ground, it's about 10 to 15 centimeters wide. So there's a good chance for many of these points that you're going to actually pick up multiple surfaces. So if you can think about how hard it is to collect that facade data, that if we can pick up multiple points from the same beam, we're going to be able to vastly enrich our data set. In terms of coverage itself, we're obviously working with the problem that this is line of sight technology. So if the laser can't see it, it can't find it. So if it's the back of the building or it's being interfered with because of a taller building in front, obviously this becomes a problem. But by using a 2/3 overlap approach in conjunction with that 45-degree turn, we're able to increase the coverage by about 50%. We've started to now use genetic algorithms, and by rerunning this, although we've not reflown it, we think we can pick up about another 25%. So by just tweaking it, not even changing the amount of time in the air, we can get more. If we take a look here, this was the actual 2015 flyover. Each of those blue little squiggly lines is the helicopter in the air. So there were 41 of them. We were supposed to have 42, and you can see here the pilot missed one. But in the end, we got quite good data. So what I'm about to show you initially, so this is most of our study area in downtown Dublin, and you'll see first what would be considered quality state-of-the-art LiDAR, which would be 35 to 50 points per square meter. So in this case, you see a bit, you can see the buildings, you can see where there's vegetation, and you can see the roads, but you don't see a lot more. With the work that we've done, we've completely transformed the process. And what you'll be seeing now is our data. This is just the LiDAR. And it's good enough that you can pick out the cars, you can pick out the utility lines, you can pick out the curbs, and all of a sudden this becomes a real game changer. So as I mentioned, this data is now publicly available. It's, I think, in 24 tiles, and the 41 flight strips all can be downloaded separately or together along with the oblique imagery that goes with this, along with also some video. And that's just through the NYU library on their faculty data repository. And now we have something we can start to work with that becomes meaningful. So you can imagine something like this actually transformed into a computational model. It's quite full in terms of the coverage. It's quite good in terms of its detail. So if you wanted to do something like microclimate modeling, you wanted to do pedestrian wind modeling, you wanted to look at pollution dispersion, blast modeling, all of a sudden you start to have geometry at a level that becomes meaningful. One of the challenge then becomes, how do we automate the rest of the process? And for some tasks, this is quite easy for computers, and in others, it is not. And so what I'll be showing you is actually a picture here in London. So this is actually buildings on top of the Whitechapel Underground Station. I had a student over here working with Crossrail, and all those little red marks are actually damage that were supposedly caused by pushing the tunnel underneath. And what you'll see in blue is kind of a rough estimate of where each of these buildings stops and starts. For the human eye, trying to distinguish one building from the next is quite easy. For the computers, it's quite difficult. And even using something like machine learning becomes a pretty big challenge in terms of finding that separation where if there's not a clear gap. So some things are quite easy to do and some things are quite difficult, and this pulling out one building from the next still remains a major problem. If there's elevation changes, if there's a gap, we can easily do it. But the most recent international contest on this for these kind of buildings showed only a 65% success rate. So what we've tried to do with this is we've tried to go backwards. So because I'm not a geomatics person from initial training, I think I look at a lot of these problems quite differently. The geomatics community has generally taken the position, more data is better. And you put it all together and then you try to find things. And what I think has distinguished my research group from some of the others that have been working in these kind of problems is that by taking an engineering approach and taking just that single flight line and looking at that data. So you can see here, it's that line of sight. Obviously, the helicopter is here, so the backs of the buildings aren't being collected. But what we're also seeing is there are places where the data is just missing, that we know it should be there, but it's not. And maybe it's not coming back because it's a window or some other reflective surface, or sometimes it just doesn't come back. So in cases where we have multi-returns, we generally think of this as vegetation. But here, where we're missing that return, what we've done is we've simply built it back, just in a very crude way, just through an initial interpolation of the next 2 points. And we said, what does this give us? We know there should be something there. So how does this help us? And by taking something very simple like this and running a contour analysis, all of a sudden, all those buildings in red, or building groups I should actually call them, we can now find in a robust way that we couldn't without that data. So again, just going back to really data-driven solutions, we can often at least make advancements in our progress in these areas. Once we've found our buildings, what we're generally looking for is trying to capture the detail boundary of the geometry. And a lot of the work in this area, both on imagery and LiDAR, has restricted itself to some fairly simple buildings, rectilinear buildings, or buildings with rectilinear openings. If we take a look here, this is the Rubrics building on the Trinity campus. It's one of Dublin's oldest ones, and if you were very fortunate and you're an older faculty member at Trinity, you might have rooms in this building. But it's a fairly complicated building. So you can see here we've got a very complicated roof line and irregular windows, both in terms of shapes and in distribution. So a lot of the geometric primitive and shape-fitting functions that people have developed don't work terribly well. What we've done is we've taken this and we said, all right, we're going to take all these points, and there's 2.6 million points, and this is actually lifetime processing, and we're going to create strips, and we're going to then look at these strips, and then we're going to basically treat them as 1D lines, and we're going to harvest the endpoints. So this is a slicing method, and from that, we've developed a very fast, pretty robust way of getting this geometry, and then we're able to then just feed this into, as a solid model, into a commercial program and basically apply Delaunay triangulation. So here, this is a facade, and it's obviously in 2D and not in 3D, that's completely automated in the process, goes directly into a commercial finite element model, ANSYS, Abacus, Plaxis, whatever you're working with. Where the real advantage became is over the existing state of technology where people were trying to take this and put it into some type of CAD program using geometric primitives and trying to come out the other end. And what you can see in the bottom here is that typically what would happen is that areas that were openings were mistaken as solid and vice versa. And it required a lot of manual intervention. The models weren't watertight. You can imagine as buildings exist over many decades, if not centuries, they deform, things change. So we need to have techniques that are robust in how they can handle these kind of problems. So some of these are fairly easy, and you can think about then extending this kind of model into a 3D, which is what the PhD student who's working on this currently is doing. In the end, again, we're hoping to be able to do some type of city scale modeling. Here I've cheated, I've just taken my LiDAR data and I've created a voxel around each. So I've taken basically a 3D box around each point. Here, this is looking down Dame Street, one of Dublin's more busy streets. These are all double-decker buses. We have a lot of vegetation. This is the central bank building. And if you look very carefully, there are a few points in the air. We think these are actually birds that got caught in the scan. So, for a lot of engineering problems, we're looking for features and details that are much more specific. And we're also working with buildings that are quite complicated, not just flat facades. So we have to develop techniques that can handle multi-plane buildings. We'll be looking at here is 34 College Green, another heritage structure in Dublin. And it's got balconies, and what may not be fully clear is that these two flanks on the side are actually set back a bit. From a structural engineering point of view, it's very important for us to be able to pull out that main facade to do our work on. Here the student has applied a grid fitting technique where they've voxelized the building, they've applied ransack within each cell, and then done kind of a clever version of a region growing to go around the corners. And it works fairly well. We have that nice back recessed facade, our front facade, and then all that architectural detailing up front. But sometimes we want to get even deeper in. We want to get each individual brick and mortar joint, or for us, often importantly, we want to be able to pull out the window frames. Because if you accidentally count the window frame as part of the window opening, then when you calculate the stiffness of your building, the building will appear more stiff than it really is. And if you do something like push a tunnel underneath, you will get a non-conservative result. So you will think you're going to get less damage than you actually would. Similarly, for energy modeling, it's quite important in the most energy models to understand what is the actual window opening versus the facade opening, and what is that window frame. So here, we're simply using a technique based on the intensity, that energy backscatter back, to pick out not necessarily what the material is, but where there's a change in material, because often those window frames are different, and the brick and the mortar is different from each other. And that provides us a good start, and it gives us an insight as to how to do this. And based on the fact that using not just the direct intensity measurement, but actually the standard deviation of these intensity measurements, that we were able to fairly robustly determine one material from the next, we said, well, what about using hyperspectral imagery? You know, would this move us forward? So hyperspectral imagery has been used very extensively in the agricultural industry, looking at plant monitoring, things like this. And we said, well, how does this work? So we teamed up with a group up at the University of Bergen in Norway, and went up and we scanned some buildings. And through various filtering mechanisms here on the bottom right, we can see that in general we can do a pretty good job distinguishing one material from the next. But where this becomes really interesting is at an even more local level. So if we look at a structure like this, we've got a brick wall. Clearly there's been some repair, or something has happened here. You can see the kind of fuzziness in the brick. These bricks look like either they were slightly different or laid in a bit of a different way. But until I get really close to that building, up on a scaffold and stuff, I'm not going to know a lot more. So from the ground level, there's only so much I can do. Yet I'm going to want to understand more about this structure. Is it going through some type of crisis? Is it going through some type of moisture retention? If I'm trying to put it up for heritage listing, you know, what of the material that's in there right now is actually original? And I can't know any of that from this information. But when I apply the hyperspectral imaging, all of a sudden I get a whole new image. Now, we don't know exactly what this correlates to, but we know that there's definitely something different there. So based on this information, we've now gone back to the lab and we've started to actually fire our own bricks, mix our own concrete, and under very, very controlled conditions, change variables. What is the firing temperature? What is the clay mixture? What is the cement to water ratio? And we can start to see at somewhere above a 95% accuracy level that we are able to determine one material from the next, even within these small strength change bands. And where this becomes really useful from a civil engineering perspective is finding defective material. So for instance, in New York City, there was a huge scandal about 5 years ago where a testing company that did testing reports for concrete, where the concrete would be tested on site, or samples would be taken on site, and then this testing lab would report back whether the concrete was good, was found to be conducting widespread fraud and had just been, you know, reporting whatever. And the city of New York had tens of thousands of tons of concrete that had been placed, and they don't know if this concrete is good. Maybe it's all fine, but they don't know. And so with a technique like this, where you know that all of this material should be the same and should have been placed at the same time, theoretically, we should be able to come out, scan it, and identify areas of difference, and then based on that, start to do some contact testing, like with a Schmidt hammer, where you're looking just for change in strength in a non-destructive way, and then based on that, actually come in and do some destructive testing. It then becomes at least financially viable to do something like this. So we're pretty excited about our recent work in this. Also, if I want to create a city-scale computational model, I need to know what at least the range of those material properties are. And this becomes really a challenge, even in the most basic sense, because most of the buildings you see around you, they have beautiful facades. But what you may not know is that the quality of the workmanship and the quality of the materials probably differs quite significantly from the facade to the back. And the further back you go on the building, the likelihood is that the quality of those materials and the masons who put them in were a lot less. The companies tended to put the good guys and the good materials in front, and the guy who was drinking for breakfast and those broken bricks and things like that ended up in the back of the building. So even if you do destructive testing, which you're rarely allowed to, that what you're testing may not be representative of the whole building. So to have a technique that you can rapidly come in and do this kind of evaluation becomes really useful. The final step for us in terms of those computational models is, what does the interior of the building look like? Where are their interior walls? And again, we're going back to this problem that there's no documentation for tens and hundreds of thousands of buildings in these urban areas. And in the tunneling community, this becomes just a major problem, that people, even if they know the tunnel's coming through, they don't want the companies to come in and do inspections. They just don't want you in. And in a recent case, there were letters sent out to 200 building owners and occupants, and access was granted for 6 buildings. So they're not going to let us in. And how do we start to estimate things like the stiffness of the building in a more robust way? And for that, we need to know, are there shear walls? Where are the positions of these shear walls? These kind of things. And there's an interesting artifact that happens in our data set. If you download it, you'll see that there's actually a layer of points that appear to be underground. Now, in Dublin, like in London and New York City, there are cases where there are actually steps down to basement units, but you'll notice that there's actually a lot more points than are there. So what's happening, in fact, is the scan's going in through the window, bouncing around, and it's then taking a really long time to come back because of this multi-bounce effect. And because the position is determined based on the speed of light and the timing, when it gets plotted in these programs, it appears as if it's further away than it really is. And we've been working with Andre Velton at the University of Wisconsin, trying to extend some of his peeking around or looking around corners project to LiDAR data for this multi-bounce. And we're hoping to make at least some progress in this area. But despite whatever we do, there will be things that we know are unknown. As a geotechnical engineer, I'm fairly comfortable with this concept because when we test or we prepare for a project, we do not have a continuous soil profile. We'll take a boring, we'll dig a hole in one place, and then maybe 200 meters away, we'll do another one. And we've got to interpolate between there. The community uses kriging and some other statistical techniques, but there's always this unknown. And so how do we then start to build that unknown into these models? And the data you're seeing here actually came from quite an infamous tunneling project in Puerto Rico. It was the first underground project there and ended up in a huge lawsuit back in the late 90s because the soil layering was quite unusual. So Andrew Whittle from MIT was kind enough to share this data with us, and we've been trying to actually build in this statistical uncertainty into the computational models through Latin hypercube and a Monte Carlo simulation as part of the actual computational modeling. But in the end, whatever challenges that we succeed in will ultimately depend on being able to handle this data. And I'd like to report that the image on the right is not my office. So if we don't store this data in a way that is accessible and reusable, it's of limited use to any of us. So in the same way that in a library we're storing our fiction by author's last name and our nonfiction by Dewey Decimal, we have to come up with systems of organization. The data indexing that's been developed to date for spatial data, things like octrees and R trees and KD trees, and you're seeing an octree here where we're dividing the space into 8 quadrants and then recursively going down either through a preset number of recursions or simply by setting an objective function like no square or no cube can have more than 5,000 points because the cache memory on my computer can only handle 5,000 points. Becomes a pretty flexible, good data system to do this in on a standalone computer. Okay, so if you look here, our colored image shows that data, the raw data, and then here we show the storage of it within the octree. And you can see that there's a pretty good one-to-one correspondence there because the octree is only storing where there's actually data. So when we put this into something we've called a data flower, we're using just a Gephi program to try to show the relationship between the points in the storage system. We can see that we have a fairly non-uniform distribution of the data and a non-uniform distribution of the storage. When we move to something like an R tree, so here, same data set, but here we can see in that storage that it's now storing this whole block, this whole bounding box. And you'll see here when we do the Gephi that you end up with a uniform distribution of the data in your index. So it says that your spatial usage is taking up a lot more. And if we go down to our KD tree where the data index actually splits and stores every individual point by itself, that the only way I could actually get this to show is actually, oops, sorry, by decimating, sorry, there we go. Oh, where are we going? Let's see. Decimating the data twofold. So it's a very intense data set. So we don't have a really good set of tools for trying to understand how these indexes will work. And what we need to now do is to get a better understanding of them because none of them were set up for distributed computing. And which means that it randomly will assign a chunk of data to a computer, it will process it, and send it back. And where that data set relates to another data set, either next to it, above it, or below it, there's no relationship. And yet the spatial reality is streets are continuous, buildings are continuous, and we need to start developing indexes that will take advantage of the distributed computing, but also acknowledge that interrelationship, that these data sets are continuous. So this becomes a focal point for some of our current work as well. And I'd like to just close by showing a quick application area. So we're going to travel a little further through our data set, and we're going to move over to a building that's actually the tallest building in Dublin. Don't laugh, it's only 17 stories. But it was actually the center of a planning permission controversy and a lot of very unhappy hearings. And this was building's called Liberty Hall, and it's owned by one of the trade unions, and they wanted to renovate it and to add a few stories. And because this is right along the Liffey here, it's a very windy area, and the community really protested adding any stories to this for the fear of it becoming even windier. So there was a wind study done by ARP, and as part of that, the decision was to not grant planning permission. And we thought this would be an interesting thing to look at about how useful would it be to have this kind of LiDAR data, this high-quality LiDAR data as part of the process. Because if you know anything about how pedestrian wind comfort modeling is done, they generally use what they call an LOD1, a level of detail 1 building. So you're just using a very simple geometry, usually a rectangle. And then we said, well, if you had more of the building geometry, not just of that building, but of the surrounding buildings, would you get a more accurate result? So this is ongoing work. You can see here on the left-hand side where the student is looking at a hybrid model. This is actually a bridge. This is the Liffey. And he's looking at trying to understand which buildings do you need to fully model and which ones can you get away with maybe just having a highly detailed model with one of the sides, or as you move away from your target building, which ones need to be included. And as just an initial study, you'll see on the right-hand side a group of 9 buildings, and just very simple, this LOD1, and we run the wind through it. When we put on a shaped roof, what would generally be considered a level of detail 2, we start to see that the wind pattern hasn't changed, but the intensity has increased quite a bit. And now when we put on our balconies in the bottom, all of a sudden we have a change in wind pattern and also a greatly increased magnitude of the wind. And I think that this gives you kind of a concept of where the value of this kind of work might come into play. And I'd like to just, I guess, leave you with one thought, is that there's so much data out there. The estimate is that basically 80% of all data being generated today has some type of spatial component. And I think the challenge that academics face and that places like the Turing Institute faces is how do we start to really benefit from that? How do we harness that? How do we vertically integrate the usage of that data? And I think that's where institutes like yours can really play a shaping part. So I'd like your thanks today.